All right, you guys. Hi. I wanted to make a video myself to help you review for today's quiz over stoichiometry. And so, stoichiometry, the basic thing you need to know is that you will probably have a chemical reaction and you're going to have to switch the moles using the mole ratio. And so, this is what we used in Chem 1 to do that with the mole map. But you will have that kind of situation. Now, looking at the equation sheet, the ones that will probably this apply to the most are anything in the gases, liquids, and solutions section of the equation sheet. So remember that N on this equation sheet stands for the number of moles. And so um, like you could apply it with the PV equals nRT equation. You could apply it to um, molar mass, which is kind of what this one is. And you could apply it to density and then solve for moles, or molarity, which is moles per liter. So all of these equations, this could be applied to, okay? But just take it one step at a time. So see what information you're given first, and then see how you can convert it to what you need it to be. So I pulled up this example problem from an old quiz that I used to give in Chem AP, where it kind of practices this. So gaseous C2H4 reacts with O2 according to the following equation. What volume of oxygen gas at STP is needed to react with 3.90 moles of the C2H4? Okay, so let me see. Yep, I can write. The thing that we need to know is that since we want to know the volume of the oxygen at STP, that we will have to convert the 3.90 moles of the C2H4 into moles of O2 before we can then solve for volume. Okay, because if you just took the 3.9, it wouldn't be the correct type of volume. So since it's starting with moles, we don't have to use molar mass to start, but we would just take our 3.90 moles of C2H4. Sorry for the terrible handwriting. I'm writing this on a computer screen. Um, and we will multiply by the mole ratio. And so it's what we want over what we have. And we want to know about the O2, and there's a 3 coefficient in front of there. And we'll divide by 1 mole of the C2H4 because there's a coefficient of 1 there. Okay. And so that is going to switch us to moles of the O2. Now, um, from this point, there's two ways to do it actually. When you get the moles of O2, then you could use the PV equals nRT equation. Oh gosh, that's still there. Sorry. But you could do that because once you know the moles, we could solve for volume, plugging in things that you know for pressure and for temperature and for R. Or the other thing you could do is STP conditions follow mole map. So we have this thing that's called molar volume, the 22.4, that you could multiply by and get the answer. But I want to go with the PV equals nRT just so you see something different. Okay. Is that going to do it? Click that. Nope, it's not. I'm having some problems here. There we go. Okay. So when I take 3.9 times 3, I did not do this without it. So I got 11.7 moles, and this is moles of oxygen gas. Okay. So now I'm going to use that 11.7 moles and solve for our PV equals nRT. So STP conditions, the pressure is 1 atmosphere. This is something you should probably just know. And the temperature is 0 degrees Celsius or 273 Kelvin. Okay. And then our moles we just solved for was 11.7 moles. And R, since we're dealing with the atmospheres, that's the 0.08206. You have to be careful there on the equation sheet to pick the correct R, but it's because we have atmospheres. That's the one that you choose. And so now we can plug in and solve for the volume. So we've got 1 ATM times the volume is equal to 11.7 times 0.08206 times the 273. So the volume divided by 1, yep, is 262.1 liters, because when you're using the volume in this equation, it's in liters. And so then 3 sig figs would just make it 262 liters. Okay. So this, I just wanted to show an example of how maybe you start with the mole ratio and again get the moles that you need and then use it in a different application. You could also do it the other way where you could maybe solve for moles first with this equation, and then after that you could then do the mole ratio, and you might throw in molar mass in this, you might throw in Avogadro's number, you might throw in even like energy and that kind of stuff too, but it all kind of applies. So I wanted to just do a quick example with you. I apologize for the terrible video quality, but it is what it is. I hope to see you soon. Bye.